Okay, we'll get started. In this section, we're going to be going through 3H. So 3H is going to be featuring the gravitational force. So we've talked about the force of gravity a little bit. Now we're going to talk about it in more detail. So the force of gravity pulls all objects with mass towards each other. So it could be any two objects. So it could be small planet, large planet, it could be the moon and the sun, it could be you and a paperclip sitting on your desk. Basically anything with mass, there's going to be a force of gravity between objects with mass. Again, the force might not be that strong, but it's definitely there. The other thing to keep in mind is that if you're close to the surface of a planet, right, you're close to the surface of a planet, that force of gravity has a specific name. And you've heard it already, it's called its weight. So again, if you look at the force of gravity for an object and it's right on the surface of a planet, we're going to say that that's equivalent to that object's weight. So that's a specific situation when dealing with the force of gravity. And you've seen that before, the idea of weight. It's also important to realize that, okay, Newton's third law, there's action force and reaction force are going to be the same size. So the two objects, any two objects, right, with mass are going to exert an attractive gravitational force. So attractive meaning that they're pulling towards each other. And again, that force is going to have the same magnitude for each object. It doesn't matter which object's bigger than the other, which one has more mass. Just by the third law, they're going to exert the same force of gravity on each other. That's important to keep in mind. So when you're dealing with the force of gravity so far, you've used this equation. You've used, okay, force of gravity, aka the weight is going to be the mass times little g, right? This equation works for the weight of an object, for figuring out the force of gravity when something's sitting on the surface of a planet. Now what we're going to look at is a more general equation, so we can calculate gravity basically anywhere. We can calculate it between, two small objects sitting on a planet. We can calculate it between the Earth and the Sun, the Earth and the Moon, whatever we'd like. So we need a more general equation to calculate gravity. And that's going to be right here. It's called Newton's law of universal gravitation. So that law of universal gravitation is going to describe how big that force of gravity is. And it's right here. It's not too bad. We're going to go through what each thing means. So we have the force of gravity on this side. That's equivalent to the following. It's equivalent to the product of the two masses of the objects. So M1 and M2. Actually, let me draw it here. There we go. So let's say this is M1, M2. So the force of gravity between these two things is going to be equivalent to the product of the two masses, M1 and M2. It's going to be, and then it's going to be divided by the square of the distance between them. So it's important to note that it's the distance between the centers of those two objects, not from the surface of the two objects. So the distance between the center of one and the center of the other object. And the last thing is, what is this G? This G is the gravitational constant. So this capital G is always going to be the same. It doesn't matter what planet you're on. If you're not on a planet, if you're in the middle outer space, that's always going to be the same. Big G is always going to have the same value. It's going to be 6.67 times 10 to the negative 11th, and then, or 10 to the negative 11. And then it's going to have these weird units, newtons times meters squared over a kilogram squared. So again, that big G is always going to have the same value. So it's important to just note that this equation, what it's basically saying is, okay, if mass goes up, the force of gravity is going to increase. And it's also saying, well, if you increase the distance between the two objects, that force of gravity is going to decrease. It's going to go down. So that's really what it's saying. It's saying, oh, the force of gravity is dependent on, the mass of those objects that you're dealing with, and then how far they are away from each other. That's effectively what it's saying. So that's all the notes, really. So just a couple reminders about the force of gravity and talking about the equation by which you can calculate gravity, that always works. It's a little more universal than just the weight formula. So now let's see a problem that uses this information we got right here. Okay, so see if you can solve it first. Again, make sure you write out your knowns and unknowns, draw a picture, write down the required formula. All of that's helpful before you see a full-out solution. Okay, let's take a look at it. What do we have? We have a Honeycrisp apple, 82 grams, is 6.40 times 10 to the 6 meters from the center of the Earth. The apple weighs 0.9 newtons. What is the mass of the Earth? So let's take a second. I'm actually going to draw this over here. So what do we have? We have the Earth. We have an apple. I'm going to call the apple M1. I'm going to call the Earth M2. So we know the mass of the apple. We know M1. We don't know M2. We're looking for M2. And we do know the distance between the center of the apple and the center of the Earth. So let's write some of that out. So we know M1, mass of the apple. It's 0.082 kilograms because it's 82 grams. We know D is 6.4 times 10 to the 6 meters. And we know how much it weighs, right? How much it weighs, that's the force of gravity at the surface of a planet. It's going to weigh 0.9 newtons. And we're looking for M2. We're looking for what's the mass of the Earth, basically. So again, how do we relate these? How do we get M2? This part should be fairly obvious. So there's really only one equation that's going to tie all these together, and that's universal gravity. G M1 M2 divided by the square of the distance. So we just need to plug, well, let's take a look at it first. We're looking for M2, and we do know M1, we do know G, because G is always constant, it's always going to be the same. We do know D, and we do know FG. So if we just plug everything in and we're careful, we're going to get out M2. So we have the force of gravity, 0.9 newtons. We have G is 6.67 times 10 to the negative 11 times M1. We have 0.082 kilograms times M2. And then divided by the distance squared, 6.40 times 10 to the 6 squared. So we just got to undo this. We just got to undo the algebra. We're just careful. So the first thing we're going to do is I'm going to multiply both sides by the denominator right here, the 6.4 times 10 to the 6 squared. Be careful that you carry through the square. So what is this going to be? It's going to be 3.28 times 10 to the 13 is equal to 6.67 times 10 to the negative 11 times 0.082 times M2. So it's the next line, and then the very last thing, I'm kind of going to combine two steps. I'm going to divide this number right here, the left side, by these two numbers by the product of these two numbers. So I'm just going to divide 3.28 times 10 to the 13 divided by these two numbers, 6.67 times 10 to the negative 11 times 0.082. So I'm going to divide this number here by this, and I'm going to get out M2. And when you do that out, again, I would be, if you're getting a, when you're doing this, I'd be careful. You make sure you put the parentheses in, so you're going to get out the right number. So put the denominator, put these two numbers in parentheses, or multiply them out first before you divide. So we're going to get out the mass, M2, the mass of the Earth is 5.99 times 10 to the 24 kilograms, kg, standard unit. And that's the answer. And if you actually look that up, that's pretty close to what the mass of the Earth is. So again, it looks like a lot of stuff, but very important to just know, like, it comes down to the same things as most other problems. Do you have your knowns? Did you correctly identify your unknown? Did you figure out the equation or equations you need? And are you clean with how you're doing your algebra out? So that's the problem. Looks like a fair bit, but just it's the same ideas as a lot of other problems. So make sure you have this solution down. Make sure you have all of the notes down. And that's it for now.